Hi everyone, this is Mr. Scott, and this is your Momentum Review Screencast. So at the top of the screen right now is pretty much the entire gist of the chapter. The fact that momentum is conserved without an external force acting on a system, we can set the momentum before equal to the momentum after. So in this chapter, the thing that most students will screw up if they do is trying to apply the right equations at the right times for the right word problem. And in the chapter, we've had 4 basic types of problems that we've done, and the pretest roundtable was a good representation of all 4. And I'm going to try and show you on this slide exactly where you've seen all 4 in the past parts of the unit. So first things first, momentum is always equal to mass times velocity. So on the test, we'll probably give you a couple easy questions asking like, if we change the mass, what does it do to the momentum? If we change the velocity, what does it do to the momentum? And just realize that those are always directly related to each other. Now, mass and velocity, though, are not directly related. They're indirectly related. So as we learned in our moving inertia lab, if there's a mass that is larger, and the force that's applied to both of the carts is equal, that mass should move at a slower velocity. Now, the first type of problem that we're going to talk about is impulse problems. So I tell my students that the second you see force or time in this chapter, we know immediately that we have to use our impulse equations. And that impulse equation is, of course, just equal to force times time, but it's also equal to change in momentum. The change in momentum is always going to be the final momentum minus the initial momentum. And one important thing to note is that in many cases this momentum might be 0. So you need to pay attention to whether we're starting at rest and the initial momentum is 0, or we're coming to a stop and the final momentum is 0, and then plug into the equation accordingly. But don't forget that action-reaction pairs still exist due to Newton's third law, and that will help guide your thinking that, yeah, there are forces that are involved, and the direction of those forces should make sense based off of whether we're bringing something to a stop. You're probably going to have a negative force that you solve for, or if you're speeding something up, you'll probably have a positive force that you're solving for based off of what was considered positive and negative in the beginning. So if you hear those 3 words, change in momentum in a word problem, or you hear force and time, you know it has to be an impulse equation that you need to use. Next up are explosions or separations. So the old cannonball and cannon we use many times in class, but for this one, we always say that there's a combined mass in the beginning. Now that combined mass could be moving, it could not be moving. So you have to pay attention to whether the left side of the equation is just going to become 0 if both masses are still and there's no total momentum, or whether they're both moving in either the positive or negative direction in the first place. So this also is what we did in the moving inertia lab, so feel free to go back and look at the moving inertia lab and the moving inertia quiz to better understand explosions and separations and all the concepts we asked you about in that quiz. Lastly, make sure that you realize that anytime there's an explosion or separation, the 2 momentums that are created afterwards are always going to be going away from each other, and one is going to have a negative velocity or a negative momentum, and you may have to plug that in when you're solving for whatever we ask you for. The third type of problem we've covered in this chapter are inelastic collisions, and this is the reverse of an explosion separation. So you had one combined momentum beforehand in explosion separation that separated into 2, and here we're taking 2 separate momentums and combining them into one as they either stick, tangle, gets caught. Something is going to happen to make these 2 masses now travel as one, going in either direction. And you've seen different situations of inelastic collisions. So sometimes the 2 objects are coming towards each other, and we have to make sure we make one of the velocities negative. Sometimes, like our dart lab, we had one of the objects still, and the other one collided into it and then combined afterwards. So pay attention to what's happening before with the velocities, and that'll make it easier to substitute and solve for whatever we're making you find on the test. Okay, and the fourth type of problem we can have in the chapter is elastic collisions. So here, nothing is sticking, but we're bouncing, and we're starting out with 2 momentums, and then we're finishing with 2 momentums also. So elastic collisions tend to be more difficult for students, which is why we waited to the end of the chapter to tell you about it, because the velocities for both masses can change. And they also can be positive or negative depending on before or after the collision. It just all depends on the situation. Here in this slide, we're showing you a V1 and a V2 on the before side of the equation, but we're also showing you a V1 prime and a V2 prime on the after side. That's the notation we like to use, but you might want to switch it to make it initial and final, just something to tell yourself that this happened after the collision versus before the collision. But that's it, guys. That's the entire chapter in a nutshell. We might ask you questions about what applies a greater impulse, something coming to a stop or something changing its direction and going back from where it started. Things like that. But outside of that, the free response part is just going to be one of these 4 types of problems, and it's going to be your job to pick the right one and then substitute in correctly. So let's try a couple practice problems off of the sheet that Mr. Kim made for all of us last year. Let's look at number 7. All right, and before we do anything, let's just identify the type of problem we're looking at, and then we'll try and set it up and solve for here the resulting velocity of the cannon. So take a couple seconds and think about which problem it is, and then I'll tell you the right answer. So if you chose explosion/separation, you win. And the reason why we know this is because it's the old standby cannon and cannonball that are going to start as one combined mass and then separate out away from each other in 2 opposite directions. Now we can also assume, because it wasn't told to us that there was an initial velocity, that we probably started at rest with both the cannon and cannonball. So here I've added the initial setup of our equations for an explosion separation situation. And now that's half the battle. The next half is trying to substitute in correctly for the right variables and figure out which variable we're solving for. So take another couple seconds and try and figure out which velocity we actually want here in your head. Now your answer to that question depends on what you call M1 and M2. If I decide to call the cannonball M1 and the cannon M2, then I'm solving for the cannon after the explosion has happened, which means that I want V2 for my variable that I need to solve for. It's also important to note that the initial velocity of both of these was just 0. So that means this velocity here is going to go away, and so is the whole term when you multiply anything by 0. We also have to take into account that the cannonball was given to us as a positive velocity of 400 meters per second. So if we decide to call the cannonball's direction positive, then there's a good chance we're going to end up solving for V2 and get a negative answer because it's going the opposite way. I'm going to put up the work to solve for this problem, and then you guys can look it over here in a sec. So when you check out the work, notice that the velocity did end up being a negative answer, which makes sense because it should be going the opposite direction of the cannon. And notice that we're also going to label with units. I did not include my units here in the work because I was going to run out of space, and I even had to trickle down to number 8. But always on your test, make sure you include the units so that way it just keeps you in the right frame of mind for what you're solving for. Okay, the last problem we're going to try here in the tutorial is number 9 on the practice sheet. And again, try to say to yourself, is this an impulse problem? Is this a elastic, inelastic, or an explosion/separation problem? And I'll give you a couple seconds to decide. So the key wording in this problem is stick together. These 2 pucks are going to become one combined mass and travel at some new velocity. So therefore this has to be an inelastic collision. Now in every single inelastic collision problem we've given you in this chapter, it's always been 2 masses that have become one combined mass afterwards. So here we're going to do the exact opposite of the explosion separation setup and put the left side of our equation with 2 momentums and the right side with a combined momentum and a combined mass. Again, let's think now, which variable are we solving for? So we want how fast the 2 pucks travel after they stick together. So take a couple seconds to think about it. And if you got this right, you should say this last velocity with the 2 masses now combined. Okay, so I'm going to show off the work here in a second, but feel free to pause the video and try this problem out yourself, and then you can hit play again if you want to double check the answer. Alright, so in solving the problem, we got lucky here because one of the velocities is 0 in the first place. So that means that we can actually get rid of the m2 v2 term altogether, and then just take the negative momentum that the first puck had and divide it by the combined mass to get the combined velocity after they stick together. So Mr. Kim was trying to be a little tricky here by giving you an initial velocity of puck A that was negative. Now, it shouldn't matter. If we call that direction that puck A is going positive or negative, no matter what, as long as you're consistent, you're going to get full points on the test. You just have to make sure that you plug in that -3, and then when you get a negative answer for the combination of both of them as they travel at the end, that you realize it's still in the same direction. All right, that's it, kids. So good luck on the test, and feel free to come in before or after school if you need more help with these problems. Go try some practice elastic collision problems and maybe even an impulse problem or two to make sure you're ready for it, and create that note card. All right, have a good one.